Hey everyone, and welcome. So today we're going to dive deep into one of the most powerful and I think elegant features in all of modern programming, Rust's trait system. And this isn't just some feature, it's a whole philosophy that really changes how we think about writing code that's both fast and flexible. So let's get into it. For decades, this question has been at the very heart of a huge trade-off in software. We all want our code to be reusable, right? To work with many different types of data. But that flexibility has always seemed to come with a performance penalty. So the real question is, how do we get the best of both worlds? Well, the answer really starts with a concept called polymorphism. It's this quest to write code that can take on, quote, many forms. And it's the fundamental principle that lets us build systems that are adaptable, systems that can grow and change over time without just completely falling apart. So polymorphism, it literally just means many forms. The idea is actually super simple but really powerful. Think about it like this. Instead of writing a function for draw circle, another for draw square, and another for draw triangle, you just write one, draw shape. You can pass any shape you want to it, a circle, a square, whatever, and it just works. This is the dream, right? Write less code, get more flexibility? Sounds amazing, but how does that actually work under the hood? Okay, so for a long time, the standard solution you'd find in languages like C++ or Java involves something called dynamic dispatch. It's a really clever mechanism, but it comes with this hidden cost. It's a performance hit that folks in the know have started calling the Polymorphism Tax. All right, so check this out. Every single time you make one of these polymorphic calls, the CPU has to do this little dance. First, it follows a pointer to find the object in memory. Then it has to read a second, hidden pointer inside that object to find something called a virtual table. Then it has to follow that pointer to the table, look up the correct function at just the right spot, and only then, finally, can it actually run the code. This happens for every single call. But listen, here's the real kicker. That little lookup, those few extra nanoseconds, that's not the real tax, not even close. The real cost is what you lose. It's an opportunity cost, because the compiler has no idea which exact function is going to be called until the program is actually running. It can't use its biggest weapon, its most powerful optimization, inlining. It basically puts a blindfold on the compiler, preventing it from making your code as fast as it could be. And that's a huge performance loss. So that brings us right back to the big question. Is this tax just something we have to live with? Is there any way to get all that amazing flexibility of polymorphism, but with zero runtime cost? Can we get it for free? And this is where Rust just completely changes the game. So Rust's answer to all this? It's the trait system. And please don't think of traits as just a fancy word for interfaces. They're not. It's a totally different way of thinking about abstraction, and it's all built on this idea of a formal contract that the compiler enforces. In classic object-oriented programming, you'd say a circle is a shape. Rust flips that. It thinks more in terms of what something can do. Think of it this way. When a type implements a trait, it's literally like signing a legal contract. The trait lays out all the rules, all the obligations, and the compiler, it acts like this super strict, tireless lawyer that checks every single line at compile time to make sure you've held up your end of the bargain. No loopholes, no exceptions. Okay, now this is where the genius of the system really shines. Rust doesn't just give you one way to do things. It doesn't force you down a single path. Instead, it puts the power back in your hands, the developer. It gives you a deliberate choice. You get two different ways to get polymorphism, and each one has really clear trade-offs. So by default, and this is huge, Rust gives you that polymorphism for free. It's zero cost. It does this through a process called monomorphization. It's a big word, but the idea is simple. Instead of one generic function, the compiler actually creates a special-made, super-optimized copy for every single type you use it with. So when your code actually runs, there's no lookup, no indirection. It's just a straight-up, blazing fast function call. The tax is gone, poof, eliminated. Okay, but you might be thinking, what if I really do need that runtime flexibility? What if I need a list that holds a bunch of different shapes? Well, for those exact situations, Rust says, no problem. You can explicitly opt in to dynamic dispatch using the dyne keyword. This creates something called a trait object. And yeah, it uses a vtable, just like in other languages. The key here is that you are making a conscious choice. You're telling the compiler, yep, I know there's a cost here, and for this specific case, I'm willing to pay it. So let's put that choice side by side. It's pretty clear, right? On one side, you've got static dispatch. That's your default. You get maximum performance, zero cost. The trade-off? Yeah, your final program file might be a bit bigger. And on the other side, you have dynamic dispatch.
This is what you opt into for that runtime flexibility, but you're knowingly paying that little performance tax to get it, and you get a smaller binary.
But let's dig into this a little more. All these rows are important, but the one at the bottom, the principal, that's the heart of it. Static dispatch is all about zero-cost abstraction. You get to write beautiful, high-level, abstract code, and you pay absolutely nothing for it at runtime. It's incredible. And dynamic dispatch, that's the pay-for-what-you-use philosophy. Flexibility is there when you need it, but it's not forced on you everywhere else. So you see, choosing between these two isn't just a tiny syntax thing. It's a big architectural decision. You're making a clear statement about what matters most in that part of your code. And this idea, this power, it doesn't just stop with your own code. This whole philosophy of contracts and explicit choices, it's like the DNA of the entire Rust ecosystem. It's what allows thousands of libraries to all play nicely together.
Let's look at a perfect example, serde. It's Rust's legendary serialization library, and it is just a masterclass in this contract-based design. It defines two key contracts, a serialized trait that your data agrees to, and a serializer trait for the format, like JSON or whatever. And here's the magic. Your data structures know nothing about JSON. And the JSON library knows absolutely nothing about your specific data structures. They only care about the contract that connects them. The result? It's mind-blowing. It means hundreds of different libraries with their own data types can be turned into dozens of different data formats, and it all just works, with no code changes and, you guessed it, zero-cost performance.
And it's not just serde. We see the exact same pattern in Tokio, Rust's async runtime. The whole async await world is built on these contracts, like the future trade and the async read, async write traits for I/O. This is what lets you write this really clean, high-level networking code that can talk to a secure TLS stream over the internet, or, just as easily, talk to a simple little in-memory buffer for your tests. It doesn't care. As long as the other end honors the contract, it just works. So what's the big takeaway here? It's this. Traits are the connective tissue. They're what allows Rust's core values, safety, speed, explicit control, to scale across thousands and thousands of libraries. The architecture of the language becomes the architecture of the entire ecosystem. It creates this incredibly cohesive, incredibly performant world. And that really leaves you with a powerful question to think about, doesn't it? What happens to the software we build, to its quality, to its performance, when the developers behind it have to stop and consciously choose the costs they're willing to pay? It's a really powerful idea to think about. Thanks for joining me on this.